Okay, I'm going to go through the second and third practice exam questions uh, that have to do with the actual second exam. So I'll skip the stuff from exam one on this exam, our exam one, and I will skip the stuff on the third practice exam that has to do with stuff we haven't covered yet. Okay, so this first page is legitimate for our second exam. Select the most acidic solution for each part. So part A, we have a concentration of protons, a concentration of hydroxide ions, and a solution with a given pH. Obviously, these are three different ways to measure the acidity or alkalinity of a solution. So in order to compare apples to apples, need to put them all in one thing or another, so we can either put them in all pH, POH, concentration of protons, concentration of hydroxide. So let's just do the concentration of protons. And so if we just go to the last one, in order to turn H plus, or pH into H plus, it's 10 to the minus pH. So if I do that in the calculator, 10 xy 5.9 negative equals. And so we see that is 1.258 times 10 to the negative 1, 2, 3, 4, 5, 6 times 10 to the minus 6. That's what that is. And so just comparing that to this, they both have the same exponent. But this has a proton concentration that's higher than this. So between these two, the first column would be the correct one. In order to turn this into a proton concentration, remember that the product of hydroxide times proton is going to be equal to the Kw, which is 10 to the minus 14. So we can get the proton concentration by dividing 10 to the minus 14 by that concentration there. And so again, calculator wise, 1E14 minus, and then we divide that by 2.7 times 10 to the 6th. And so it looks like we're getting something cut off here, but 1, 2, 3, 4, 5, 6, 7, 8, 9. So we're at a very small concentration of protons, which we probably could have done without the math, because if we have a hydroxide concentration of 10 to the minus 6, that's going to be greater than 10 to the, it's going to be, closer to 10 to the minus 8th for a proton concentration. So mistakenly, I've circled that in describing it, but that is clearly going to be the most acidic solution. Okay, so for part B, we have two different putative weak acids. And so we have concentrations that are the same. They're both 0.1 molar. And so you can determine the more acidic solution by which has the larger Ka. Again, these are equilibrium constants, products over reactants. And so the acidity will be whichever one has ionized to a larger extent. In other words, whichever one has the highest equilibrium constant. And so you have to first go to the exponents. This is 10 to the minus 4. This is 10 to the minus 3. 10 to the minus 3, whatever the number in front is going to be bigger than 10 to the minus 4. So this will ionize greater and be the more acidic solution. And so now we have a couple of problems looking at the molecular structure and the strengths of acids and bases. And so, again, some of these you can't compare directly. So let's just look at the first two. We have hypochlorous acid and chlorous acid. And so this one is going to have more oxygens, more terminally positioned electronegative atoms. And so that will weaken the bond to the proton. And so between those two, hypochlorous acid is the stronger acid, so that most acidic solution. And again, these are all the same concentration, right? And so then you just have to compare that one to this one, which is bromous acid. And the molecular structure of these, you could tell probably without having to draw it out, will be identical. But here we'll have a central chlorine, here we'll have a central bromine. And so the only difference between those two, since neither one of them is bound to the proton is going to be the electronegativity of that central atom. Chlorine is more electronegative than bromine, so we go with chlorous acid as the most acidic solution. All right, and so in D, which is the most acidic? Well, we've got two acids that are strong acids, and then we have another one which isn't on our list. If you don't know what hydrogen sulfide is or its capacity to act as an acid, in this case, all you need to know is that one's not strong, so we didn't remember it, and those two are. And so we did talk about the periodicity of these binary acids, and so as you go down the periodic table, you'll get to the stronger acid, and so hydroiodic acid. I think they're in a different order on the key that you'll see posted on the website. But anyway, that's the stronger acid. All right, question 2, indicate the equilibrium pH for the aqueous solution of each compound. And so here we have a series of compounds. We need to assess whether they're going to turn the resultant solution acidic, alkaline, or nothing. And so the first one is an ionic compound, so it's not lithium carbonate, it's lithium and carbonate. And so the cation, again, if it's a molecular cation, it's acidic, so this is not. It's a metal cation. Lithium is in the alkaline metals, and so that will be pH neutral, so that is not going to have an effect on pH. Carbonate, we go through our sort of mental flow chart with anions. Is this the conjugate base of a strong acid? The answer is no, and it is not the conjugate base of a polyprotic acid, which means the only thing this is going to do is act as a base, and since that was pH neutral, we'll have an alkaline solution. Iron 3 perchlorate, so again, ionic compound, you take them separately. Iron is a transition metal, so that will act as a Lewis acid. Perchlorate is the conjugate base of a strong acid, perchloric acid, so it will be pH neutral. Iron will be acidic, and so that will give us a pH of less than 7. Another ionic compound, so sodium, hydrogen sulfate. Sodium's an alkaline metal, so it will be pH neutral. Hydrogen sulfate, again, is this the conjugate base of a strong acid? The answer is yes, which means it's not a base. But then the next question, the flow chart, is it hydrogen sulfate? Yes, it is. So this one will be acidic. And then this is not an ionic compound. We did the structure of this in lecture. This is methylamine. And so it is not ionic. It is a molecule, and there's a lone pair on that nitrogen. So it will act as a base, and so therefore it'll give you a pH greater than 7. All right, which of the following will make a buffered solution? And so what we need to make a buffered solution are similar members, or similar concentrations of each member of a conjugate pair. And so if you just look at the molecules that are similar in each sort of column here, here we have sodium nitrite, and here we have sodium nitrate. And so in each case, we've got additions of either strong acid or strong base. And so first of all, the sort of central molecule we have to add, it has to be either a weak acid or a weak base. And so since we're dealing with sodium salts of anions, we're going to ask whether these molecules themselves are weak bases, or the other way to think about it is, are the protonated versions of these two different molecules weak acids? And so looking on the right side, nitrate, the acid that would be with that, nitric acid, that's one of our 7 strong acids, which means that no matter what we add to it, there's no way any of these things can be buffers because we're not dealing with a weak acid or a weak base. Nitrite would make nitrous acid, HNO2, so that's not one of the 7 strong acids, therefore it's a weak acid. And so now we need just to pick the one that's going to give us similar concentrations of both A and HA. And so here we have a weak base, we're adding a strong base to it, so that's out. Here we have a weak base and we're adding a strong acid to it, but if you look, so the concentrations are the same, so that means by adding 20 milliliters of that concentration, you know, we have that number of moles, which will be equal to that number of moles. So we're basically turning all of our A minus and turning it into HA, which does not give us similar concentrations, so that's out. Again, weak base with a strong base, that's out. All we have left, this better work. We have a weak base, and we're adding 10 mils of 0.1 molar hydrochloric acid. So that means since we had 20 mils of the weak base, we're protonating half of that. So we're going to end up with half of this quantity being A minus, the other half being HA. That sounds like a buffer to me, so that's our answer. Dihydrogen phosphate is amphiprotic, meaning can act as an acid or a base. So the conjugate base of dihydrogen phosphate means, well, let's treat dihydrogen phosphate, which is H2PO4 minus. Okay, that's what that is. The conjugate base will be the deprotonated version of that. So we take one proton away, we get hydrogen phosphate, and that'll be now 2 minus. And the conjugate acid means we put a proton on that sucker, and we get H3PO4 or phosphoric acid. Okay, so question 5 is a kinetics question. Question 6 is a kinetics question. All right, question 7, oxalic acid is diprotic with 2 carboxylic acid groups. So the first thing we need is a valid Lewis dot structure. And so, you know, in theory, you could be combining this in all sorts of different ways, but we tell you it's got 2 carboxylic acid groups. And so we said in lecture that a carboxylic acid has this. So we have CO2H. And if you look at the empirical formula here, we have that exact formula doubled. And so the only possible thing it could be with 2 carboxylic acids would be 1 carboxylic acid, as I've drawn it, hooked directly to the other carboxylic acid. Right, and then just to be complete, gotta do our lone pairs. And there's your valid Lewis dot structure. All right, so the pKa1 for oxalic acid is 1.27. Would you expect the pKa2 to be smaller, larger, the same? And so this again is a polyprotic acid, or diprotic more specifically. And so even though looking at it, they are electronically identical, we talked about this for these polyprotic acids, that even though they're electronically identical in the original molecule, as soon as one proton falls off, that anion that we'd have here, for instance, if this were the one to fall off, would fundamentally change the electronics of the other one. And so that anion would essentially strengthen that OH bond, making it less acidic, which means the Ka would go down and the pKa to go up. So successive deprotonation events get weaker, and so the pKa would go up from 2 to 1. All right, so if the equilibrium pH of a 1 molar solution is 0.686, what is the concentration of the fully protonated oxalic acid at equilibrium? So we'll just treat oxalic acid as H2A, and equilibrium pH of this other one, HA minus, and then H plus. And so we're going to go ahead and assume that the second deprotonation is not going to contribute much to the pH. Again, if I had to rewrite this question for you, I'd probably make that explicit in the question, because I recall this being somewhat confusing. But anyway, if we just consider this in the context of a rice table, so the equilibrium pH is 0.686. What's the concentration of the fully protonated species? And so the fully protonated species, what we're trying to figure out is this, okay? And so what we have here is an ice table, and this is not going to be a standard ice table. We are given that the 1 molar solution has that resultant pH, and so we call that concentration whatever it is in total, so we'll put that there. We know that in order to reach equilibrium, it's going to be minus x on the left, plus x on the right, and of course this would be xx, and that's all well and good, except we don't know. We can do all that, but we're already given the equilibrium pH, which means we can come up with, using that pH, the equilibrium concentration of protons. So again, the concentration of H plus is going to be 10 to the minus pH, which is 10 to the minus 686. So calculator, 10 to the 6, sorry, 10xy 0.686 minus, and so that concentration will be 0.206. And so that goes in here. Now, since that is that equilibrium concentration of protons, that same x value would go here, okay? And that is also the same amount of the x value that would go here. So the concentration in our E row would be 1.0 minus x, and x we've just figured out is 0.206. So 1.0 minus 0.206 equals, so just flip the sign of the calculator, add 1, and we get 0.794. And don't forget your unit, molar. Okay, so we ran into this with looking at for exam 1. What the question that's asked in the key is different than the one I have here. So I'll just answer the one here since it's in front of me. What is the percent ionization described in part C? And so this one is quite simple. It is the x value, which is 0.206, divided by the original concentration of the weak acid, 1.0 times 100%. And so you just type that into the calculator, 0.206, and this is probably pretty easy to do without a calculator, times 100, and we see it's 20.6%. Although, okay. And one more question from exam 2, and then we'll do exam 3 on a separate video. MOPS is another buffer that biochemists use all the time. Because it's got a pKa of 7.2, which means we can make buffers in and around 7. So here we're asked, we need to make a buffer, a 1 liter buffer, 0.1 molar, MOPS at pH 7. What would the ratio of conjugate base to the acid form be at equilibrium? And so again, pH equals pKa plus log of A over HA. So all this question is really asking is that A to HA ratio. So the target pH is 7, the pKa is 7.20, and log of A over HA, negative 0.20. Subtracting this from each side is log of A over HA. We get rid of the log by raising it as the exponent of 10. And that we can just plug into our calculator, so that's going to give us our A to HA ratio. And so 10xy 0.2 minus equals, and so that ratio is 0.63. 1.365. Okay, how many moles of sodium hydroxide would need to be added to 1 liter of a 0.1 molar MOPS buffer to make not of a buffer, of a 0.1 molar MOPS solution to make the buffer at 7, assuming the change in volume is negative. So we've already figured out our A to HA ratio of 0.631. And now again, we talked about this in class, 1 liter, 0.100 molar MOPS. This is the A plus A. So A plus HA equals 0.10 molar. And since it's 1 liter, we can call that moles, which will make this real easy. So what it's basically saying is that we're starting out with 100% of the HA, and we have to deprotonate some of it to get to the A, such that we have this ratio. So all we need to really solve for is the moles of A, because that's going to be the moles of NaOH that we need. And so you just solve these two equations for each other. So this one becomes A equals 0.631 HA, which we can plug into this, 0.631 HA plus HA equals 0.1. Add those together, 1.631 HA equals 0.1. HA equals, so 0.1 divided by 1.631. I gotta clear the whole thing, sorry. 0.1 divided by 1.631 equals 0.0613. In order to get the A, we just have to, subtract that from 0.1 according to this equation. So the A is going to be 0.0387, and that's the answer we can put in here, 0.0387 moles. Okay, so we will make another video with the Exam 2 material that is on the third practice exam posted on the website.